What's great now is that we now have the implicit function theorem, and we can use it to make qualitative statements about economics. So we can use, and kind of loosely quantitative as well, the IFT to make qualitative statements about economies. And the general prescription for this is, well, we're going to write down a system of equations that represents the economy. We're going to find the equilibrium, and that'll give us a point on some constrained space. And then we're going to study the derivatives of all the quantities near the constrained space, and that tells us how the economy evolves as we change quantities. So let's do an example. So suppose we have two consumers. We'll call them 1 and 2. In an economy, consisting of two goods, say where we'll parameterize those by x and y values. And where 1 and 2 have endowments so they start the game with E1 of good 1 and just E2 of good 2, respectively. So player 1 in this economy, or consumer 1, starts with E1 of good X, and player 2 starts with E2 of good X. So whenever we do analyses like this, we have to make certain assumptions in order to actually carry out the analysis. But usually the goal is, of course, to make sure that the assumptions are not too ridiculous. So to do analysis, we assume that U1 and U2 represent we'll call it satiation functions. For consumer 1 and consumer 2. So this is kind of a maybe a little bit weird assumption, but we also assume that we have the same satiation function for both good 1 and good 2. So that's another thing. But in order to be a satiation function, right? We assume that U1 and U2 are concave, and that boils down to ui double prime is strictly, and they're strictly concave, strictly less than 0. And so examples of this are, say, a parabola pointing down, right? And in particular, if I have the parabola function, right, there's a sweet spot for my satiation. If I have exactly this amount, then I'm the most happy. But as I get less or more, I'm kind of less happy. You know, say milk, right? If I don't have a whole lot of milk, I'm not so happy, maybe. But if I have way too much, then I don't know what to do with it, and I'm also not so happy. That gets stressful, right? So that's maybe milk. So this would be like minus x squared, say. And usually we make it positive somehow by add some positive constant. Another potential function is log x, right? Where my satiation increases monotonically but very slowly. So actually this would mean that I want more of it, but I don't get a whole lot from getting more and more and more, right? Because if you notice, the derivative of this guy is 1 over x, so that means that as x is increasing, the marginal satiation that I get from having this satiation function is getting smaller and smaller and smaller. So it looks flatter and flatter and flatter, that satiation curve. So at some point I'm just like, well, do I really need more of this? That kind of thing. So assuming that those are satiation functions and they work for both of the goods, it's just the psychology of the consumer, if you want to say, we set capital U of I, x I, y I, equal to alpha u I of xi plus 1 minus alpha ui of yi, where xi is how much consumer I gets of good 1. Yi is how much of good 1 or good 2 consumer I gets. These are, of course, my satiation functions, and alpha is just some parameter (0 is less than alpha is less than 1. And we call UI, capital UI, xi, yi. It's hard to distinguish between capitals and non-capitals here. Probably should have used a different letter. But here we are now. So we call UI of xi, yi the utility function of consumer I. Right, I want to maximize this thing, and so we assume that we got our satiation function, but alpha basically controls my preference for goods, right? So if alpha is really high, then I really have much more of a preference for good 1. I want to get that the most satiated. Whereas over here, if I decrease alpha, that means that I want good 2 a lot more. Because then my function is, I get more from maximizing this, right? So the whole point is to maximize everything. Now, note the Cobb-Douglas function is part of this class. And I think you'll be showing that, and the hint for showing it is ask yourself a question. Why is the log of a utility function also a utility function? So ask yourself that question. So the Cobb-Douglas actually can be represented exactly like this guy right here, which is nice. So that means that this kind of utility function does show up, and it's not crazy to think about it. So now consumer I maximizes the utility subject to so consumer I maximizes utility subject to Pxi plus Qyi equals value of endowment I, right? So P is the price of good represented by X. Q is the price of the good represented by Y. And when I come to the market, I only have my endowment, right? And essentially I have the value of my endowment, right? And so what I should be able to get of my goods should be equal to exactly this equation, right? So this is a income constraint, essentially, right? It's a simple linear constraint, this income. So that's great. So these are the prices of the goods. So we can actually compute this. We can actually compute what that maximum should be subject to this equation. And we're going to talk about this later. We're going to talk about how to do this later. So I'm going to write down exactly what it is. But later, we shall show, and then when we do this, we'll be using, so this is a foreshadowing, Lagrange multipliers, which Lagrange multipliers are a really cute optimization trick. We'll show using Lagrange multipliers that, well, du, capital U, dxi, evaluated at xi, yi, divided by du I dyi xi yi, which is of course when you work this out, this is alpha ui prime of xi divided by 1 minus alpha ui prime of yi. Well, it turns out that this is equal to P over Q. And that is really fascinating. And it's kind of magical, because what does this represent? This quantity is the internal relative valuation That is, it's what the consumer believes is the relative value between these two goods according to their utility function, according to their psychology. And this quantity here is simply the external relative valuation. And this is exactly the relative valuation set by the pricing, the external market. So that is actually a really, really fascinating development, right? So you wouldn't necessarily know that unless you solve this equation. But it turns out that that is exactly what happens. So this is kind of a little bit magical, almost. So this is just the case, and we can use that now. So using this, first we want to do some simplifications so that we have a system of equations, right? So since all valuation is relative, of course, we just set Q is equal to 1, so we eliminate one of our variables on the system. Then we have a system of 6 equations. Right, where we want to maximize, we want to solve for all the values of my system using what we have here. The first equation is from consumer 1's, the equation for consumer 1's maximization of the utility function, and that, when you unfold it, is alpha over 1 minus alpha u1 prime of x1 minus p u1 prime of y1 is equal to 0. The next equation is the condition for the max of the second consumer, x2 now, minus p u2 prime of y2 is equal to 0. So that's the same equation, except it's different utility functions potentially, because I have different consumers and so they have different psychology. Well, we've got p x1 plus y1 minus p e2 is equal to 0, right? So this was the equation that says that the price of good 1 times the amount of good 1 plus the price of good 2, which is we've set to 1, times good 2 that consumer 1 gets, is equal to the total valuation. The total valuation is the price of good 1. This should be good 1, P1. This is E1. The price of good 1 times the endowment that consumer 1 brings. So this is essentially the price of the goods that consumer 1 brings to the market. And the same thing for consumer 2 plus y2 minus, but now consumer 2, right, had good 2, so this is just E2 is equal to 0. And then we have, of course, the market only has what people brought to it, so the total amount of good 1 and good 2, good 1 in the system is E1, because that's all that consumer 1 brought to the market, and the total amount of good 2 is also going to be E2, because that's all they brought to the market. And usually we set it up as looking like this homogeneous system, just for convenience sake. Now, if we set both endowments, so let's set both endowments E1 equals E2 equals 0. So both of these guys bring the same amount of good to the market. right? So I have the same amount, and the only thing that's going to change, maybe, is the price of the good. Well, the unique solution, so this system actually has a unique solution to this system is, well, we have x1 equals y1 is equal to alpha. We have x2 equals y2 is equal to 1 minus alpha. And we have p is equal to alpha over 1 minus alpha. So you might be saying that, well, how on earth did you get that this was the unique solution? And well, these are a bunch of linear equations, and so it's fathomable that we would actually get unique solutions. But when we have these non-linear utility functions or derivatives of the utility functions, we might find ourselves concerned. But the fact is, right, so we use the fact that u double prime of I is less than 0, and so u I prime is monotonically decreasing. Right? So this is the derivative of u prime of I, and so this is monotonically decreasing. And if it's monotonically decreasing, then you can argue that, well, we have to have, if you look at these equations, we have to have essentially that x1 is equal to y1, and x2 is equal to y2. And once you have that, you can solve this system of linear equations and figure out exactly what all the values are supposed to be. And in the next video, we're going to actually, at this equilibrium, we're going to ask, well, what are derivatives of the different quantities as we change the prices of the goods, or the endowments of the goods?